In this video, I'm going to demonstrate an applet that shows you what a confidence interval for one proportion means. First, go to the website rossmanchance.com/isi-applets.html. Across the top of the page, you'll see links to other applets. We're choosing the applet Simulating Confidence Intervals. Here in the screen, there's a number of graphs that are going to be filled in automatically with a couple of clicks of a button. So first, under the method, we are going to pick proportions and binomial and walled. They may already be pre-filled for you. And then there's 3 more boxes and then a button called sample. Then there's a confidence level percent and a recalculate box and then a sort and reset. So let's go through. We're going to put in some numbers into these boxes to create some confidence intervals through this website automatically. So the first box that we're going to fill in has the letter pi next to it. So that's the Greek letter pi. And oftentimes pi represents, in some textbooks, but not in other textbooks, pi represents the population proportion. So the funny thing is that if you are a statistician going out to collect some data, you do not know what your population proportion is. It is unknown unless your population is, say, like 50 people, and then you can actually get a hold of everybody and compute a population proportion. If that's the case, why are you doing statistics? You just have your parameter. This is more useful when the population is so large that you can't estimate it. For example, estimating the true proportion of people who would vote for a candidate or not. It would be pretty impossible to get to everybody in your entire population and then be able to calculate that proportion. Certainly, it wouldn't happen fast or very cheap. So this pi represents your population proportion. I'm going to leave it at 0.5, so 50%. There's a 50% chance of getting a success on surveying someone and then them answering a question. The next box is n, little n. That is for your sample size. So how many people are you going to sample? Right now it's at 100. I'm going to change that to 10. So we're only going to sample 10 people. And intervals, that means how many confidence intervals do you want to create? I want to create just one with my one sample. So the next box down tells us what confidence level do you want to use. By default, it's probably 95%, so I'm going to leave it at 95%. All right, now we need to actually calculate a confidence interval. We could do this by hand by looking at the p-hat and then the z-score and then the standard deviation and come up with an interval. But I'm just going to push sample, and what happens is some of these tables start getting filled in. So in the upper right box, we have the outcomes from our 10 people sampled, and we have how many were failures and how many were successes. So in this sample, we had 1, 2, 3, 4 failures and 1, 2, 3, 4, 5, 6 successes. So that means that p-hat is equal to 0.6. So the graph below it has graphed that number 0.6. It put a little green box to say our first sample was a sample proportion of 0.6. Now over here in the middle of the page, there is a faint green line. It's pretty bright, and there's a little dot right in the middle. That dot represents our sample proportion of 0.6. If you look down towards the axis, that little dot hovers above 0.6. So the dot represents the center of our interval, and then when you add and subtract the margin of error, you come up with the endpoints of your confidence interval. So these green lines represent the margin of error. You've added margin of error to the sample proportion and you come up with an endpoint. It's maybe 0.9-ish. And then from your sample proportion, you subtracted the margin of error and you came up with a lower endpoint, maybe about 0.3-ish or so. So the whole length of this green interval is margin of error plus margin of error. It's actually 2 margins of error. The center of your interval is your p-hat. So the question is, when you create a confidence interval, your goal is to use sample data to estimate what happens with the population. And you hope it's a good estimate, but you never know because you don't have your population proportion. Unless, of course, you have set up this applet and then you know your population proportion. But in the real world, you don't know your population proportion. So you've made an estimate for your population proportion. You've given it some wiggle room. And then we can look at this, magically, suppose we know the population proportion. We look at the population proportion of 0.5 and say, oh, hey, it landed within the interval. So actually, our guess of 0.6 is pretty okay. Our confidence interval captured the actual population proportion. So that's just one confidence interval. That first confidence interval happened to be pretty okay because within the bounds of the interval, we captured the population proportion. Let's do it again. I'm going to click sample one more time. And there we go. Here we've clicked the sample again, and actually it looks like I did click it a second time, but I got the exact same numbers. So that's why I didn't see anything change. Now I've done the confidence interval 3 times for my running total. The proportion ended up being 0.3. I can see from up in the upper right here, I only have 3 successes and a lot of failures. My data point has been graphed down here. My one interval has been plotted over here, and it looks like the sample proportion of 0.3, when you go out to the left and right to the margin of error, it also does capture the population proportion of 0.5. So I'm going to keep doing this. I'm going to click sample again, and you can watch the number of successes change from sample to sample. And you can watch, oh, did you see that? The interval is no longer green, it's actually red. Look at the sample proportion. Let's go back to the upper right. It's 0.2, so only 2 successes out of the 10 when we should expect to see about 5 successes out of 10. So there are 2 successes out of 10, that's a 20% success rate. Add and subtract your margin of error through the confidence interval formula that you can find in the textbook. And when you subtract the margin of error and add the margin of error, it is so far to the left, because it's so far below 0.5, that the endpoints of our interval have actually not crossed over the 0.5 line. So the upper endpoint of our interval is maybe 0.45 or so. It's actually not capturing the population proportion. So we did get one sample that was not a very good representation of our population. Now, how do we know this? Well, because we rigged the game to say, let's pretend the proportion is 0.5. We only know we messed up because we know 0.5 is the population proportion. This one sample, if this is the only thing you did, your estimate of the population proportion would actually be pretty far off, but you'd never know it. So I'm going to speed this up a little bit because we got, 13 samples were taken total, and 11 of them had green bars, and we only had 2 of them with red bars. I happened to catch us on the second one. So if I keep pushing sample, you can watch where the center of the interval lands. There's another red one. Let's speed this up. I don't want to make 1 interval at a time. Let's make 10 intervals. Now I see 10 confidence intervals have been created. So we took 10 samples, we got 10 sample proportions, we created 10 confidence intervals, we graphed them all on this number line, and we can see that 3 of the intervals did not cross over the center line of 0.5 that we had rigged the game to be the population proportion. 7 of the intervals did cross over, so they would be close enough estimates of the population proportion. Let's increase this even more. Let's look at 100 intervals. So we're making 100 95% confidence intervals. So sample. Now you can see in our graph all of these lines. So every green line represents the dot in the middle was the sample proportion, and then adding and subtracting the margin of error. Then we had a second sample was too high. It did not capture the population mean. So that interval is just not a good estimate of your population. Here's the third one, here's the fourth one, here's the fifth one. You can see how the centers all kind of vary, and once they get too far out to the sides, the intervals no longer cross the middle section. But as long as your sample proportion kind of is in the middle-ish of all of these numbers down on the axis, then your interval will cross over that median line. Another way to look at it is down here in the sample proportions. These stacks of green dots, everything that's green represents an interval that crossed over the line of 0.5. Any of these red dots represent the sample proportions that were too far to the sides, and their intervals did not cross over 0.5. You can see them here. There's one of them that was a 0.2. Here's the one interval. The sample proportion was 0.2. Here's 1, 2, 3, 4 intervals that had a center of 0.8, and there's 1, 2, 3, 4 of these 0.8 proportions that didn't have the width to cross over the middle. They did not capture, those 4 intervals did not capture the true proportion for the population. So let's think about this. We were making 95% confidence intervals, and look at all the intervals that did not capture the center line of 0.5. 1, 2, 3, 4, 5. No coincidence there. The whole idea of a confidence interval is that if you make 100 intervals, 95% of those intervals will cover the center, the population proportion. 5 of those intervals will be bad guesses. They'll be too high or too low and will be bad estimates. Now, whenever you make a confidence interval, you don't know which of these 100 intervals you've made. You only have one. You just have to know in the back of your head, well, 95% means that this could be one of the 5 that is a bad estimate of the population proportion. So let's check out something else that is a little different. We had a sample size of 10. I want you to change the sample size to be 100 or something larger than that, and then take a sample of another 100 intervals. What did you notice? Let's try that again. Here's a sample size of 10, so n is 10. Run your sample. There you go. Now choose a sample size of 100. What do you notice? There's some big changes happening here. Here's another thing that I want you to notice. Change the confidence level from 95 down to 80. So there's 80% confidence intervals. Actually, let's reset here. Let's start all over again. Oops, it doesn't let me do that. Type in 80. All right, we're going to start fresh. Here's n. Let's do an experiment here. I've clicked the reset button, and we're going to do some comparisons. Let's let a sample size of 100 be chosen. Proportion is 0.5. We'll make 100 intervals, and the confidence interval is 80%. If we sample 100 intervals, you can see what's happening to these confidence intervals. You can see how many red bars there are, how many red intervals there are, how many green intervals there are. What's the connection between an 80% confidence interval and the reds and the greens that you see in this graph? Let's recalculate it. Let's click sample again so we have a larger running total. As you click sample over and over again, look what happens to these calculations down here. Here's individually on the last 100 confidence intervals, this is the proportion that contained 0.5, the center. And then here's our running total. We've done 800 intervals overall. Look at this proportion and see how it changes. If I keep pushing sample, what do you notice about that proportion? So I'm up to 2,300 intervals created. What do you notice about that percent? All right, another question that I want us to look at. I'm going to reset this. I'm going to change, let's see, we have 0.5 for the proportion, and we have 100 for the number of samples. We are going to make 100 is the sample size. We're going to make 100 intervals. I'm going to change my confidence level to 95%. And then sample. So in this part of the activity, I want you to look at what happens when you change the confidence level from 95% down to 80%. What just happened to the confidence intervals? Go back to 95. Pushing recalculate. What do you notice? What happens to the actual graph with the red and green bars? What happens to the intervals containing pi? So you don't have to resample here. You can just click on recalculate. You can also get a feel for what happens by looking down here in the sample proportions. Look what's red, look what's green. When I change the percent to 80 and push recalculate, what do you notice? Why does that happen? Let's reset this and let's look at one other interesting fact. I'm going to keep 0.5, 100, 180 right there and sample my 100. Take 100 samples, create 100 confidence intervals. I'm going to change my sample size from 100. I'm going to change that down to 30. And take a new sample. What just happened? What did you notice happening? I can click sample a number of times. Now let's go back to change n back to 100. There's a subtle difference that happened here. And I want you to observe all of the confidence intervals in this graph and describe what you saw happening.